Welcome to the second part of the lecture on RSA algorithm. Let me first systematically recap RSA algorithm, and before that let me define the notation properly. We need the following parameters. We know that M denotes the plain text or message, C is the ciphertext. What is N? As we discussed in previous class also, that we will be basically transmitting the message in integers. The message M will be some integer. We will be using decimal rather than the binary numbers, but definitely we need to convert it into binary number. So what is the maximum number such that maximum number N such that the number of bits used to represent a block of plain text is less than or equal to N. So N is that number of N is that integer that when we represent the integer with binary in the binary form, so that will be the maximum number of bits required to represent the block of message. Because we discussed it previously also that plain text is encrypted in blocks where each block is having a binary value less than or equal to some number N, that is the binary value of N actually. So this will become more clear when we will do some example. In addition to this, we need two more numbers, E and D. So E basically stands for encryption. This is something which sender should know, okay, and this is something which receiver should know. And basically E is for encryption, so this is used at encryption part, and D is for decryption, so this is used as at decryption part, okay, which will also become clear when we do the example. Now we talk about some assumptions on what should be known at what level. So this value of N must be known to the both transmitter, sender, or the receiver, okay, it should be known at both. In addition to that, sender knows the value of E, and the value of D is only known to the receiver. Now let's see what makes the public key and private key in terms of public key cryptography. Recall that public key is something which is known to both the parties, and it can be known to all other parties also. So what is known to all is N, and E is known to the sender. And if you see the private part, then this N comma D together forms the private part, okay, because it is known to the receiver only. Now let's see how this RSA algorithm works. RSA algorithm is based on some algebraic results in number theory, so it is in that sense a little bit involved. Let's first articulate the major requirements of RSA algorithm. It is possible to find the values E, D, and N such that M to the power ED modulo N is equal to M for all values of M which is less than N. So we have already defined that this N is actually sort of upper bound in terms of what should be the block size of the plain text. So this is one important major requirement needed in RSA. The other two requirements are, now before explaining point number 2, it is very important to understand, as we have discussed it in the general concept of public key cryptography, that the encryption process should be easy, decryption should be difficult. For that purpose, we will need some computations to be easy and some computations to be difficult. Now, following this norm, the condition number 2 is it should be easy to compute, relatively easy to compute the quantity M to the power E mod N. Okay, we will explain it in detail that what it actually means. And also it should be easy to compute C to the power C to the power D modulo N, of course for all values of M less than N. Okay, we'll see it in detail what it means actually. Now the third condition, which will be very useful in defining the private key, is that given E and N, given E, it should be difficult to compute D or infeasible to compute this D. Now the question will remain that what does these operations mean? That is computing M to the power E and C to the power D. So answer is that we know that what is M. M basically denotes the message. Okay. Now what is the main job of encryption? We need to convert this into ciphertext. So M to the power E, since M is an integer, okay, and E is also a number which we have chosen. So M to the power E, and then we will do it modulo N. Okay. Since transmitter knows E, M is the message block, and N is also fixed known, so we can compute this operation. So whatever will be the result, that is your C, the ciphertext. Okay, so this is the ciphertext. And the decryption, how to do that? So we'll do C to the power D modulo N. So this E, D and N should be chosen such that this gives you back N. Okay, so this is the decryption. So now how to choose it? We need some results from number theory, although I will provide a supplementary video separately which will briefly describe those results. We'll use those results here. Okay, now you see we can also write it like this. So this C we can write as M to the power E, then to the power D mod N, which can be written as M to the power ED mod N. Since we are doing modulo N, C is also computed using modulo N, so this operation is fully valid. Now look at the requirement. So we need that M to the power ED modulo N should be equal to M. This we can also write as M modulo N, because we know that M is less than N. So now what do you observe here? From number theory, you know that this means that E and D are the multiplicative inverse of E. Okay, the video, a supplementary video on number theory explains this. But let me give here one example. You know from basic mathematics that if you have any number x, then its multiplicative inverse y is defined as if you multiply x and y and the result is 1. In normal numbers like rational numbers, it is very easy. Suppose you have any number 3, its multiplicative inverse is 1 by 3, because 3 into 1 by 3 is 1. Fine. But in modulo addition, this multiplicative inverse is defined in general in modulo way. Okay, like this here, that any number, suppose M to the power ED. Okay, so this modulo N is equal to M. So from number theory we'll we have already defined in the class also one function called totient function phi of N. Okay, and a supplementary video on number theory we will do this, that what does it mean that ED are multiplicative inverse, means ED modulo some number. So here the number is phi of N is equal to 1. Okay, which is equivalent to saying that ED is equivalent to 1 in modulo phi of N. In other words, D is E inverse in modulo phi of N. Okay, so this operation by given E and N, then finding D in this way, this operation should be infeasible. It is possible to find D, E and N such that this operation becomes very difficult to do. Now again, as per one result which will be provided in the supplementary video of number theory, that E and D are multiplicative inverses modulo phi of N if they are D and E are relatively prime to each other. Okay, so I will state it here. And what does it mean in terms of greatest common divisor or GCD? We know, from the definition of GCD that this means GCD of D and phi of n should be equal to 1. Since D and E are relatively prime, so we can also say that GCD of E and phi of n should be equal to 1. Now here are the ingredients of RSA scheme with keeping all this in mind. Okay, so it's here. You need two prime numbers P and Q. Take product of those two prime numbers, and now these P and Q are chosen in private way. Okay, that is, it's only the person who chooses it. Suppose I have to transmit something, it's me who is choosing this P and Q. Then I multiply these two prime numbers, I get n. This is publicly distributed, it is calculated. Then when I know n, I can compute phi of n, torsion function. You know that you have to compute a number of co-primes actually. So then we find E, compute E or choose E such that greatest common divisor between phi of n and E is 1. Okay, so why this is needed? Because to form D and E as relatively prime and DE are multiplicative inverses. Then we compute E inverse modulo phi of n, and this is D. So this is also private, it is calculated and it is also kept private. Now this operation, the last operation, the inverse operation, should be infeasible, and it is quite possible to choose such numbers, choose such E and to choose such n, hence P and Q, such that E inverse computation in modulo phi of n is difficult. Now what is the public key? It is E comma n. What is the private key? It is D comma n. Okay, let me now summarize the RSA algorithm in this video, and I will publish a separate small video where I will give the example. Okay, and parallelly I am also preparing one video which will provide the ingredients from number theory which are we going to use here. So 3 separate small videos makes it better. Okay, so let me summarize the RSA algorithm. Then parallelly I will also upload the video on some fundamental results on number theory which we have used here, like what is the torsion function and what does it mean ED modulo phi of n equal to 1 and other things. So here is a summary of RSA algorithm, what it means. So what is the first step? You have to select P and Q. Okay, P and Q should be prime and those should not be equal to each other. Calculate n is equal to P into Q. Fine. And then torsion function. So in that video you will see, but I have shown in the class also that a torsion function, when you have a number whose factors are primes, the torsion function is equal to the torsion function of primes. So this is basically phi of P and this is basically phi of Q. And for a prime number, how many co-primes are there? Just P minus 1. That is, if Q is a prime number, how many co-primes? Q minus 1. So that is what torsion function is. Then select integer E. How to select it? The condition is here, GCD of phi of n and E should be equal to 1. Then calculate D. How? By taking E inverse in modulo phi of n. Then your E n forms the public key, your D n forms the private key. How to encrypt? Suppose your plain text is divided into the blocks and each block is represented, of course it will be in binary form, then finally converted into integers. Let m be that integer less than n. Then you have chosen E, you have chosen n, you can compute m to the power E and you can do the modulo with n, that is your C, the ciphertext. Now decryption at by using the aliases public key. You have ciphertext C, take C to the power D by virtue of definition by virtue of the property, the way you chose D. This way, D and E are the multiplicative inverses. Hence, when you do C to the power D, it basically becomes M to the power ED modulo N, that is back M, you get the plain text. This is the brief summary of RSA scheme, and in coming videos we will do example, as well as there will be a video which contains the basics of number theory, which are the various terms and some results which we are using in describing the RSA algorithm. Thank you.